Hello, hello. Welcome back to Pilariscon 2024. It's my pleasure to introduce our next speaker, Eloisa Perez Benes. Eloisa is a passionate modeler with a background in physics from the University of Sydney. She is currently at the Burnett Institute, and today Eloisa will present how to stop an epidemic using the Atomica Python tool. Please join me to giving a warm welcome to Eloisa Perez.
Hello everyone, I'm Eloisa and today I'll be talking about how to stop an epidemic using the Atomica Python tool. Firstly, I'd like to talk a little bit about the global impact of infectious diseases. Infectious diseases are the third leading cause of death worldwide, and this is by conservative estimates. They account for more than 13 million deaths every year and accounted for 14% of deaths from all causes in 2019. This number has only increased since the onset of the COVID pandemic. This is why it's so important for governments and funding organizations to tackle this urgent issue. However, they have limited resources, so they need to be spent strategically, especially since a big amount of the burden of infectious diseases falls on low and middle-income countries. We can use mathematical modeling tools to simulate outbreaks and public health interventions, and this can help us to determine the best course of action and maximize our impact. So firstly, let's have a look at a simple disease model. This is known as the SIR model, susceptible, infected, recovered. So people start off in the susceptible compartment and they have some chance of becoming infected. So they flow into the infected compartment through this arrow. And they flow there at a rate mediated by the infection rate. Then once they're in the infected compartment, they can also flow onto the recovered compartment with some probability, and this flow is mediated by the recovery rate. This is a compartmental model, the basis of which is this structure we see here, with compartments containing numbers of people and flows, where people flow from one compartment to the next. We're actually going to add a little more complexity in our version of this model that we're going to use for this presentation. So firstly, we're going to add births, and we're also going to add deaths. But we're going to have two death rates. Firstly, a death rate due to infection, and also a death rate due to other causes. So how do we actually model something like this? Well, this is where Atomica comes in. Atomica is a Python simulation engine for running compartmental models, such as this one. It's used not only for modeling infectious diseases, but also for pregnancy complications, climate change impacts, and many more. It's highly configurable and easy to use, thanks to all of its inbuilt functionality, which gives support for running simulations, calibrating models, and implementing public health programs. So how do we actually go about implementing one of these models in Atomica? Well, firstly, we need to define the model by generating a disease framework and data. Then we can run the simulation with this information and obtain some simulation results. Then we need to calibrate these results to obtain a status quo scenario. So this is the business as usual scenario of what would potentially happen in the future if we keep doing things exactly the same way that we're doing them now. And lastly, we get to simulate alternate scenarios to see what would happen if we change things slightly. So let's go through those steps. Firstly, we need to define the model, and the first part of that is making a model framework. This describes the model structure and disease dynamics. So we're taking that flowchart that we just saw and translating it into Excel format so that Atomica and Python can easily interpret it. The model framework has 3 pages: compartments, transitions, and parameters. The first one, the compartments sheet, simply contains all of the compartments that will be available in our model. So that's what it looks like so far. Secondly, we have the transitions, detailing the arrows in our model, where people flow to and from. And it will always be in this direction, from rows to columns. And it looks like this. And lastly, we determine the parameters that will be in our model. So we've already named our parameters in the previous sheet in the transitions part, but here we're actually going to either define the values or tell Atomica where it can find those values. So in this case, most of the values can be found in the data book, so we don't need to worry about them for now. But we do have the infection rate, which is defined as a function of the number of people in the susceptible compartment infected, recovered, and the infectiousness. We can also add a couple of extra parameters. In this case, I've added the incidence, which is the flow from susceptible to infected, and the number of deaths due to infection, which is the flow from infected to deaths, but only the component that's due to infection. And now we fill in the data book. This just contains the data values, which in many cases are just estimates, for the model parameters that we've just defined in the framework. This includes compartment sizes and flow rates. These values will later be used for initializing the model, running the simulation, and then later for calibration. That's what it looks like. And I'm not going to go into too much detail because we're just filling the data values, but I will say that we have a couple of ways of doing this. We can set constant parameters, or we can also have time-varying parameters that are determined as a time series. So for example, in this case, because it's a very simple example, I've only put in a maximum of 2 data points. But say we look at the number of new infections near the bottom, we have a value for 2010 and another one for 2020. We could also have all of the years in between. So we can have whatever granularity we like. And now it's time to run the simulation. So the first step is obviously importing Atomica. And once we've done that, we can create a project, which is simply a Python object where we store information relating to our model. So everything is going to go in there. All we need to do is create a project using app.project, and using the framework and data book arguments, we simply input the file names of our framework and data book respectively. Then we're ready to run the simulation. We just use p.runsim, so the runsim method of the project object. And I'm going to give it a result name of uncalibrated. And this is what that looks like. So we're just plotting the number of people in each of the 3 main compartments, susceptible, infected, and recovered, through the years of the simulation. So we can see how they evolve at each time point. Obviously, we've still got a way to go. The simulation isn't calibrated yet, so as you can see, the simulation doesn't quite match the data that we've set. Well, in fact, it doesn't match it at all. These are the blue and red points. We only have data for susceptible and infected, so in this case, we will just be calibrating those 2. We're not going to be able to calibrate recovered because we don't have data. If we did have data on that, then we'd be able to add data points for that as well and calibrate it as well. So this is where calibration comes in. Calibration basically amounts to adjusting model parameters so that the overall simulation trends match those in the data and those that we therefore observe in the real world. This will allow us to make accurate predictions because without calibration, we can't really ensure that our future predictions are going to have any basis on reality. Thankfully, we can use Atomica's inbuilt calibration algorithm, and all we have to do is choose which parameters to adjust or calibrate and which parameters to match, measure, or calibrate to. So these are the parameters that we're going to calibrate. So on the left, we've got the simulation parameters that we want to calibrate. And on the right, we have the data points that we want our simulation to match. We're going to do this in 3 steps. So when we calibrate, we always start off with the parameters that have a bigger impact on the simulation and that impact the biggest number of people. This is because if we started, for example, with the death rate due to infection, this impacts a very small number of people compared to, say, the birth rate or the death rate. So if we perfectly calibrated the death rate due to infection, but we haven't calibrated the birth rate yet, once we calibrate the birth rate, everything is going to be out of sync again, and we're just going to have to start our death rate, our infection death rate from scratch. So instead, we start off with the population and then the general epidemiology, such as the infection rate and recovery rate. And finally, we calibrate the disease mortality. And these are the code names that we're going to use in our code. So how do we do this? Firstly, we make an empty calibration object called a parset. This simply contains a copy of all parameters, which we can then modify. This is useful because instead of modifying our original copy of the parameters, we can just modify our parset and our data book and original values stay the same. Secondly, we use Atomica's calibration function to calibrate, just like we just described. Firstly, the population, then the disease prevalence, and finally, the disease mortality. We're actually going to loop through this 3 times. So even though the disease mortality contributes a lot less to the overall dynamics than, say, the population, there can be a bit of a feedback loop. So it's good to loop through a few times to make sure that we're accounting for that feedback. And finally, we run another simulation of our calibrated model so we can observe what that looks like. And here it is. So as you can see, now the plot is actually calibrated. The simulation is actually matching the data that we've set. This is a simulation of the current status quo. But what if we wanted to analyze other hypothetical scenarios? Well, this is our last step. In Atomica, we have integrated support for implementing public health programs, optimizing funding allocation, and including budget constraints. However, in the interest of time, we're going to take a bit of a shortcut. So I'm going to focus on what public health programs actually do. Public health programs could be any sort of changes in testing, treatment, vaccination, or the introduction of a new health product, such as a new vaccine. What programs do is they affect outcomes in our simulation by modifying model parameters. So, for example, if we introduced a novel vaccine, maybe it doesn't stop you from getting a certain disease, but it could greatly increase your chances of recovering from it. So, our shortcut is going to be that instead of actually including a whole program, we're going to modify the data book to emulate what a program would do in Atomica and the results that we would observe. So what we're going to do, we're going to imagine that we have this vaccine and that it increases the recovery rate. So it actually doubles the recovery rate from 0.3 to 0.6. And when we rerun our simulation, this is what we observe. As you can see, the number of people infected has greatly decreased. In fact, it's stayed more or less constant. And the amount of people who have recovered has increased. It's not immediately obvious because the scale of the 2 plots is a little bit different, but we do have more recovered people. And we actually also have a higher number of susceptible people. This is interesting because we haven't directly changed the infection rate. However, the infection rate is a function of the amount of people in all the other compartments, including in the infected compartment. So since we've decreased the number of people infected, that also decreases the infection rate and therefore increases the amount of people who are susceptible. We can understand this intuitively by just thinking that since there are less infected and therefore infectious people in the population, there are less people to give that disease to the rest of the population. Another interesting result that we get from comparing the status quo to this alternate scenario is we can see that the number of infections and number of deaths due to disease has greatly decreased. Specifically, new infections decreased by 27% and disease deaths decreased by 34%. This means that thanks to this new vaccine, we've saved 737 lives. So I just want to make a final note. we shouldn't take the results from this modeling too literally. So just because the model says we've saved 737 lives, it doesn't mean that it's going to be exactly that in the real world. This isn't meant to be a magical crystal ball to see the future, but it does give us a bit of an insight into the disease dynamics that can play out in different future scenarios. So in conclusion, Atomica is a really useful open source Python tool used for simulating infectious diseases, and the insights gained can save lives and greatly reduce the public health impact of epidemics. If you've liked this little taster and would like to learn more, feel free to check out the Atomica GitHub and the Atomica tutorials. Since it's open source, you can even modify the GitHub repo, fork it, and edit it locally if you'd like. And in the Atomica tutorials, there's a step-by-step guide on how to use Atomica in a little bit more depth than we've been able to go into here. Also, feel free to check out these Atomica modeling studies and reports. The first one is a paper on using Atomica for tuberculosis work. And the last two links are different reports that have been made applying Atomica to tuberculosis and HIV work. And these reports actually have been used to generate recommendations to different governments on how to manage their epidemics in the country. Thank you very much, and I'm looking forward to answering your questions. Thanks.
Hey, Eloisa, it was a really good talk. Thank you so much for being here, for bringing us your expertise on this subject. And yes, thank you so much all for being here at the conference. Just let's continue enjoying the PyLadiesCon 2024.